Design of experiments is a useful methodology for process improvement. The purpose is to find a relationship between process variables we can control and key process outputs in order to increase process capability. You can use Excel statistical analysis tools, solver, pivot charts, etc. to plan and analyze the results of these experiments. The first approach is to look for a linear relationship as shown in Excel DOE. But in some cases this relationship may not be linear, in which case we will try a quadratic model with Response Surface DOE. We will use an example in this Excel file you can download. Download file Excel Response Surface.xlsm from OneDrive to your PC. In this example, we are trying to maximize process yield acting on the critical factors pH, temperature, and time. We will run the experiments in the experiments simulation sheet using coded values. We start by running a full factorial experiment with two central points. We now compute the two-way interactions by multiplying the corresponding columns in sheet factorial analysis. We now use Excel data analysis/regression. This is a confirmation that this linear mathematical model is not valid, our squared adjusted is very low and all p-values for all factors and interactions are above 0.05. We suspect curvature, so we look to the average yield values for the pH inputs with a pivot chart. We can, clearly, see the lack of linearity. Yield for pH equals 0 is totally out of line with the -1 and +1 values. In order to approximate a quadratic model, we need two additional values for each factor. In our case of three factors, we have two possible designs as shown in sheet RS designs. Both CCD and CCI designs involve the same number of experiments, 20, but in the case of CCD the two additional values go beyond the values of 1 and -1 we originally wanted to experiment. In the following table we can see the correspondence between coded and uncoded values for each factor. We cannot run CCD because the resulting pH values are physically impossible. pH varies between 0 and 14. Therefore, we will run a CCI design for three factors. To run the experiments we will need to convert all the coded values in the CCI table to uncoded as shown in sheet run experiments. To randomize the order in which to run the experiments, use a macro pressing Ctrl+O and then follow the order indicated in column I. In our case we will simulate the experiments by loading the coded CCI design table in sheet experiments simulation and we will obtain the resulting yields. We are going to use two alternative methods for the approximation of a quadratic formula to our data: solver and regression. We start with the solver alternative. Open Sheet Response Solver. The purpose of the analysis is to find a quadratic mathematical formula to approximate the behavior of our process. This formula will have as terms an intercept coefficient, three factors each with a coefficient, three two-way interactions with their coefficients, three squares of each factor with their coefficients, as shown from J2 to R2. To use solver, we start by defining where we want solver to store our results. The coefficients, they will be the yellow cells I3, 2 or 3. Assuming we already have the results, we estimate yield C, for each experiment in column F with a formula in F3 which we will replicate all the way down. In this formula, we use the corresponding factor values in columns B, C and D with the coefficients in I3, 2 or 3. Now we ask solver to calculate the values from I3, 2 or 3 to make the total error in G23 a minimum. Then we obtain the coefficients we were looking for in yellow cells I3, 2 or 3, from which we can build the formula to estimate yield. Now that we have the formula to estimate yield from pH, temperature and time, we want to find the values that will give the maximum process yield. We will again use solver, this time, to find these optimal values. Now we will use the coefficients in I3 or 3 we just calculated, and the values in I13, 2 or 13. The only values we are asking solver to calculate are the three factors in J13 to L13. All the other values, for interactions and squares, are calculated from these, with a formula in the corresponding cell. In I13 we put 1, that will be multiplied by the independent term in I3. In K15 we put the formula for yield, which is just the sum product of the coefficients in I3 are 3, and the values in I13 are 13. We ask solver to maximize yield, K15, with the values of our three factors in J13 and L13, with the constraints that they should be between -1 and +1. We obtain the optimal coded values of pH equals 0.3, temperature equals 1, and time equals 0.08. This will give us a yield equals 23.8. Another Excel alternative is to approximate the quadratic formula using regression. In order to do this, we need to build the table of interactions and squares just by multiplying the corresponding columns of the factors, as seen in sheet response regression. We can now go to analysis/regression. Y are the outputs in column B. X are the inputs in columns C to K. We include the column labels and get the results. Now we can see excellent are squared values, 0.98, and C, which factors and interactions are significant, P less than 0.05. We notice that temperature and all its interactions have no significant effects on yield, P greater than 0.05. Removing these non-significant terms, we obtain the coefficients similar to those we calculated with solver. We have a more simplified formula because temperature was not significant. This formula is for coded factor values. We can again use solver to maximize yield. We add cells R16 to R24 to house the values calculated by solver. Solver only needs to calculate pH, R18, and time, R19. R21 to R23 are calculated with a formula from these two values. R17 equals 1 to multiplied with the intercept coefficient in N17. Let's have a look at the shape of this formula. Now we can understand why the linear model was unable to find the optimal yield. We were trying to represent this with a flat surface, experimenting only with +1 and -1. The red area is where we have the maximum yield, and we can confirm the pH and time to obtain it. Another way to see it with a 3D graph. We are assuming that this mathematical formula represents our process, but there are some additional checks we should do to validate our assumptions. To do this, we are going to analyze the differences between the actual results of our experiments and the estimated values using our formula in sheet residuals. Comparing the residuals with the estimated values, we should not detect any trends. We expect the residuals to follow a normal, Gaussian distribution with an average of 0. The test for normality gives us a p equals 0.61 greater than 0.05, so it is okay, no evidence of lack of normality. No trends have been detected along the time the experiments were run. See the timestamps of each experiment. Now we make confirmation runs with our calculated optimal values for pH and time, and we obtain an average yield of 22.2, with a confidence interval from 21.0 to 23.3. These are some conclusions. Design of experiments can be used to approximate linear or quadratic models to our process response in order to understand its behavior. It allows the identification of critical factors affecting the response. With a regression analysis, we obtain a mathematical formula to estimate the process response as a function of these factors. We can then find the values of these factors that optimize the response. Very often we find a close to linear relationship between factors and response in our area of interest, then we can use a linear regression DOE. If these relationships are not linear, we can use Response Surface DOE, as we have just seen. All this analysis can be performed with Excel statistical analysis tools, solver, pivot charts, etc. Another example of nonlinear DOE, the catapult exercise. You can read this article in Polyhedrica blogspot.